Yes, student, is my screen visible?
Yes, sir.
Yes, sir.
Okay, so we will start now. So we will start with a new topic, that is the design of Clariflocculator. And in the previous classes, we have seen some of the designs of water treatment units. We have covered the design of aerator as well as the flash mixer. Uh, Once this coagulant is added in the in the water, the coagulation process starts, and the flocks are formed, and those flocks are settled and collected in the clariflocculator. So this you might have studied in the undergraduate level during the water treatment chapters. Okay. So this clariflocculator, this is a typical cross section of a clariflocculator. It has got two units. One is the clarifier and second one is the flocculator. Okay. So here you can see in this particular picture here, these are the flocculation paddles. So there are two sections. This is the flocculation, this is the flocculator, and this is a clarifier. Okay. So in the flocculator, what happens, the flocks are formed and they are collected, and these flocks, they will be collected over here, and once in a year these flocks are removed, or during the maintenance purpose. And here over the top here we have a steel gantry girder. So the basic purpose of this steel gantry girder is to provide a support to this rotating paddle, and these paddles are continuously rotating with the small speed, and it is helping the flocculation process. Okay. Once the basic travel of water is like this, so here there is an inlet pipe. Water will go up, here it will go up, and then it will come down from here. Okay. So here the flocculation process takes place, and from here the water goes in the clarifier, and here it will be collected in this channel. Okay. And then it will be transferred for the further process, mostly for the filtration and the chlorination purpose. Okay. So please draw a nice figure of this afterwards, because it takes a lot of time. So I'll be posting you the PDF of this particular PPT in the classroom. So please draw a nice figure of this. Okay. So we have to design different components of this clariflocculator. The very first component is this wall. Okay. This is the most important portion. So this wall will be subjected to huge amount of water pressure, which will be coming from inside. So it will be designed similar to your tank. Then secondly, we have a walkway. It is not shown over here, but ideally there is a walkway over here, and this walkway is provided along the periphery just for the inspection purpose. Then we have to design this central shaft. Okay. And we have to design its foundation also. Okay. Here in the wall also we have to design the foundation. Okay. Now as far as this wall is concerned, this wall is just a partition wall, and it is usually loaded from both ends, because here you see there is an opening over here. So there will be a water pressure from here, and there will be a water pressure from here. So as such there is no bending, but we have to design this for the self weight. Okay. You can see this picture. This is very much clear. So here we have two portions. So this is your clarifier, and inside this is your flocculation chamber. Okay. And here you can see there is an opening, so water from inside will come out. Okay. So it will come out like this. So you can see it is a simple separating wall. It is supported by, this is a ring beam. Okay. And there is a column over here. Okay. So we have to design this column and ring beam separately, and this wall will not be subjected to any kind of water pressure. Okay. So whatever nominal design is there, that we have to provide. And here at the center you will find this is a central shaft. Okay. So accordingly now we have to go for the design now. So let us see, this is the complete picture. So here you can see there is a gantry girder over here. Okay, so this is a gantry girder, and here we have a flocculation chamber, here we have a clarifier, and here at the end you can see here this is a channel. Okay, so from here the water is getting collected and then it will be transferred for the further process. Okay, of course this is your walkway. Okay, so we have to design all these components now. So let us quickly start with the design of this clariflocculator wall. So if you see the picture, the clariflocculator looks like this. We have a central shaft over here. Okay, and here in between there is a partition wall. So we are designing this wall. This is the most important wall, and this will be subjected to huge amount of water pressure, right? So this clarifier is already designed by the hydraulic engineer, so all we have to do is go for the structural design of this particular wall. So the basic data which is given to you, that is the height of the water. Okay, remember this is the height of the water. So height of the water is given to you as 0.38 sorry 3.5 meters, and the freeboard which we are considering, generally we consider freeboard as 1 feet, which is equivalent to 0.3 meters. So the height of the wall which is required is 3.8 meters. Okay, now here, if you see the diameters of the clariflocculator, the clear diameter of the clariflocculator is given to you as 20 meters. It is a very large diameter. Okay, usually we have designed the tanks or maybe ESR. So in that the diameter is probably 6 to 8 meters, not more than that. But this is a very large diameter, and because of this large diameter, the design is getting affected as far as AST is concerned. Okay, so that we will see when we'll go for the AST calculations. Now the basic thing which we have to assume is the thickness of the wall. Okay, so thickness of the wall which we are assuming in this case is 200 millimeters. Okay, so with this basic assumptions and the data which we have provided to us, we are going with the design now. So it is a simple wall. Okay, and it is subjected to internal water pressure, and because of this water pressure the beam, or sorry, the wall will be subjected to axial tension as well as the bending as well as the shear. So this design is very much similar to the design of the cylindrical wall which we have seen in the GSR. Okay, but these situations are little bit different. How we can see this? So as far as this cylindrical wall of clariflocculator is concerned, we have to use different tables. Okay, so we have to use table number 12, 13 and 11. If you remember, we have used different tables, like we have used table number 9, we have used table number 10 and table number 11 for GSR. Okay, so GSR has got a assumption that this base is fixed. Okay, but in this particular case the foundation is not fixed, it is subjected to some amount of rotation, so this is applicable. Okay, so why this is so? Because if you see the GSR looks like this. Okay, so there is a complete solid slab which is supporting this vertical wall, isn't it? Okay, so this is a continuous one. Okay, but as far as the foundation of this part is concerned, it is not a continuous, right? Okay, so it is going in the circular fashion, but then we have a slab over here, then we have a wall over here, something like this. Okay, so it is, some rotation is possible over here, whereas in GSR the rotation is not at all possible. So this is a different condition where the rotation is possible in the foundation. So with that a possibility, we have to use table number 12. So table number 12 is going to give you the design coefficients for tension, table number 13 is going to give you design coefficient for bending, and table number 11 is going to give you the design coefficients for the shear, right? So we will see the design for tension now. Okay, so I'm talking about only the tension part, right? So for tension we have to use table number 12 of IS 3370 part 4, 1964. Now, if you read the caption of this table number 4, it says the tension in the cylindrical circular wall with hinged base. Okay, so if you see the earlier table, it is fixed base, but here it is a hinged base. Okay, hinged base means the rotation is allowed. So it is hinged based, free at the top and subjected to triangular loading. Okay, so this is table number 12 of IS 3370 part 4 1964. So again you can see the value of coefficients, they are totally depending on a equation or the value, that is h square by dt value, and its coefficient or the actual tension can be calculated by simple expression T equals to coefficient, which has to be taken from this particular table, multiplied by W into H into R. Okay, so let us quickly see what kind of coefficient is there in our case. So here this is h square. So here h, when I say h is nothing but the height of the actual water. So here if you see, if you go back, the height of the water is basically 3.5 meters. Okay, so here I'm just going to put this is 3.5 square divided by the diameter is 20 and the thickness is zero point 0.2 meters, because here if you see, we have taken the diameter as 20 and thickness is 200 mm, that is zero point 0.2 meters. Okay, so now can anybody tell me what is h square by dt value, please? Batao.
Sir, 3.06.
It is 3.06. Okay, so this is very close to 3. Okay, and if you see, we have a row, complete row for h square by dt value as 3. So if you are getting a value in between like 3.5 or 3.6, then what we have to do is we have to interpolate between 3 and 4. Okay, but now this is, since this is very close to 3, so I am just taking the same coefficients which are there for 3. Now if you refer the coefficients, the coefficient value, this is 0.07, then it is increasing, then again it is increasing, this is again increasing, this is the maximum value. Okay, and then it will start decreasing. Okay, remember in the previous class of GSR we have seen the tension is maximum somewhere near 0.6 h. Okay, in the previous class design also we have obtained the value, maximum value as 0 at 0.6 h, sometimes it is at 0.7 h, sometimes it is at 0.5 h. Okay, so we are have to take the maximum value because we have to design this for the tension. Okay, and if the thickness is not sufficient, then you have to increase the thickness. So let us see the maximum coefficient. So maximum coefficient which is taken from the table is 0.519. Okay, so at 0.6 h, okay, this has to be measured from the top. Okay, so 0.6 h is 0.6 into, this is the height of the water, that is 3.5. ये कितना आता है? Anybody? Yes, कितना आ रहा है?
2.1.
2.1 meter. Okay, so from the top the value is coming out to be 2.1. So at 2.1 meter we are getting the maximum hoop tension, and if you see the coefficient sorry, if you see the maximum hoop tension, the equation is coefficient into W into H into R. So your coefficient is 0.519, the density of water is 10, the height of the water is 3.5, and the radius. Okay, remember the diameter of this clariflocculator was 10, was 20, so the radius will be 10. So can anybody give me the value of coefficient or value of maximum hoop tension?
Sir, 181.65.
Okay, someone please cross check.
Yes, sir.
ठीक, good. So now this is the maximum hoop tension, and we have to see the axial stress now. So axial stress can be, this is 181.65 into 10 to the power 3, because I am converting this into a Newton, and the area of the concrete. So we have assumed the thickness as 200 and the unit thickness is 1000. How much is this then? Something like 0.9.
0.9.
Again, that's
Zero
it.
eight.
908, okay, Newton per mm square. Okay, so you can see the value of tensile stress in concrete. This is direct tensile stress in concrete. It is 0.98, whereas the permissible value for M25 grade concrete, it is 1.3. Okay, so definitely we can see that the 200 thickness is sufficient enough to resist the actual tensile stress in the wall. Okay, so let us further proceed. So now what we can do, we can assume the thickness of the wall as constant, at that is 2200 millimeters throughout the height. Okay, now let us quickly see the bending. So again, for the bending we have to use IS 3370 part 4, and this time we will be using table number 13, because table number 13 is going to give you the value of coefficients for a cylindrical wall which is hinged at the base, free at the top, and subjected to trapezoidal loading. Okay, so trapezoidal loading, we have, this is triangular load and this P is the constant load, so it becomes trapezoidal. So in our case this trapezoidal load is not at all there. So what will have, you will have moment equals to coefficient into W into h to the power 3. Okay, this is not clearly visible, but this is h to the power 3, and for this purpose again we have to refer to h square by dt value, and in our case it is 3. So we will be using this particular row. Okay, so let us quickly see this. So again in this case, this is 3.5 square, this is 20 multiplied by 0.2, so this is coming out to be 3 point something 06, so which is equivalent to 3. And here if you see, now see, this is in bending. Okay, so we have to see the maximum bending moment. So maximum bending moment, this is 0.0004, then this has increased, then this has increased, then again this has increased. I think this is also increased, this is also increased, this is also increased, this is increased, but here it will start decreasing. So the maximum value of the coefficient is 0.0153, which is acting at a distance of 0.8 h. Okay, so here again you have to interpolate. If you are getting not exact value, in our case we are getting 3, you may get 3.5, then we have to go for interpolation. Okay, so the coefficient value is 0.153, sorry, 0.0153. Okay, so this is the value of coefficient. The density of water is 10, height will be 3.5 to the power 3. So can someone tell me what is the bending moment? Yes, bending moment value please.
6.56.
6.56 kilonewton meter. It's a small value. Can someone please verify this? Is it correct?
Yes, sir.
Okay. So now we have to go for check for stresses. So the bending moment value is 6.56 10 to power 6. Okay, I is BD cube by 12, so this is 200 into this will be 1000. Okay, 200 cube divided by 12. and the y will be something like 100, because the 200 is the thickness. Okay, so can anybody give me the value of stresses?
0.98.
0.98
98.
newtons per millimeter square. Someone please cross check this. करेक्ट है?
Yes, sir.
ठीक है, right. So you can see this is also well within the permissible limit, so definitely we can go ahead and we can take the 200 thick uh, wall. Okay, so let us quickly check the requirement of the thickness. So our thickness required will be depending on the bending moment. The value of bending moment is 6.56, so this value is 6.56 into 10 to the power 6. Okay, what will be the value of q? What will be the value of q?
1.527.
1.527. Okay, so can anybody tell me how much is the depth required?
65.4.
55 point,
65.54.
फिर से बोलो.
65.54.
65. Someone please cross check.
Yes, sir.
ठीक है. So we can definitely continue with 200 okay, and here the value of small d will be definitely 175. Okay, uh, this value may change. Okay, so because the diameter required will be slightly higher, so in place of this I am assuming this as 170. Okay, so 30 effective cover I am deducting. Okay, now how much area of the steel is required? So this will be depending on the bending moment value. So the maximum bending moment value is 6.56 into 10 to the power 6. Okay, sigma st is 130. J कितना आता है? 0.8. कितना आता है?
0.86.
0.86. Okay, so give me the value of AST then.
345.5.
Someone please cross check. ठीक है, वैल्यू बराबर है. Is it 345.5?
345.15.
ठीक है, चल जाएगा, कोई फर्क नहीं पड़ता उतना. ठीक है, anyway, now as far as AST minimum is concerned, till now we are using 0.24% of the cross section area, isn't it? We have used this in GSR, we have used this in the aerator design, flash mixer design, almost everywhere we are using the AST minimum value as 0.24% of the cross section area. But as far as this design is concerned, that is the design of Clariflocculator, the AST minimum value will be 0.35% of the cross section area. Now, why is this? So for this purpose, we have to refer to this minimum AST clause. Okay. Now I am just going to read out this particular clause for you. It says the minimum reinforcement in the walls. Okay. So we are designing the walls. Okay, in each of the two direction at right angles within each surface zone shall not be less than, okay, shall not be less than 0.35% of the surface zone. Okay, so this criteria is there, but we are the IS code is giving a uh, relaxation. Okay, IS code is giving you the relaxation when we are using a different kind of a steel. Okay, that is when we are using the high strength deform bars, and the minimum reinforcement, you can see the minimum reinforcement can be further reduced to 0.24% of the cross section area for the deform bars. Okay, and uh, this is applicable only when tank is having any dimensions not more than 15 meters. Okay, so when this 25% criteria is applicable, when any dimension, especially the diameter, is not less than 15 meters. So till now we have designed GSRs plus aerators which were having or which were satisfying this particular criteria because the dimensions were less than 15 meters. But in this particular case, your one of the diameter is 20 meter, so we cannot use this particular criteria. So this relaxation of 0.24% is not applicable in this particular case. Therefore now we have to use the AST minimum as 0.35%. Okay, so this is the case. So now, can somebody tell me what will be this value? That is 0.35 divided by 100 into 200 into 1000. Yes, please.
700.
700. Okay, mm square. So you see the value of steel which is required is AST minimum, and its value is 700. Okay, so please remember, in case of clariflocculator we have to use the AST minimum criteria as 0.35%. This is a very common mistake which is made by many students in the past. Okay, so please read the IS code clause correctly and then use 0.35% of the cross section area. Okay, so this is the steel which we have to provide with the in the vertical direction, because vertical direction the steel is going to resist the bending moment. Okay, now you see this particular wall will be subjected to very high tensile stresses. Okay, because the height of the wall is roughly 3 meters, sorry, 3.5 meters. So we have seen the AST required for the hoop tension. Okay, let me go back for you. So the AST required for the hoop tension will be very large, because the hoop tension value, if you see the maximum hoop tension value, it is almost 180 kilonewton. It is very large value. Okay, so we cannot provide this hoop tension reinforcement throughout the height of the wall, because this will be highly uneconomical. So usually what it is done, the coefficients which are there, so this h square by dt value, so h square by dt value is 3, and corresponding the coefficients are shown in this vertical column. Okay, so we are going to calculate the hoop tension at every level. So IS code has given the coefficient values at 0h, 0.1h, 0.2h. That is the height of the wall is divided into 10 equal parts. Okay, so here from the top we have 0, then 0.35, 0.7, 1.5, so on up to the bottom. So bottom will be 3.5 meters. Okay, so at the bottom there won't be any tension because there will be a foundation, isn't it? So all the coefficients which are there from the IS code, they are written over here in form of a column, and correspondingly the hoop tension is calculated. Okay, so hoop tension is what? Your coefficient into W into H. बराबर है ना? ऐसा कुछ है equation. Yes, W into H into R. R is also there. So here on the screen you can see the value of coefficient. This is very less value, 0.074, and the W is 10, H is your height of the wall, and this is nothing but your R. So you can see the coefficients, or you can see the hoop tension. So hoop tension at the top, it is less, that is 25.9 kilonewton, then it is increased to 62, 98, 131, 155, and so on. And here at 0.6 h you are getting the maximum value, that is 181.65. just now we have calculated this, and further the hoop tension is going to get reduced. Okay, now for this purpose you can calculate the sigma st. Okay, So AST. So AST can be calculated by simple expression, that is hoop tension divided by sigma ST. So the sigma ST value is 130. Okay. So whatever this coefficient is there, or whatever this hoop tension is there, we are going to divide this by 130. Of course, the hoop tension is in kilonewton, so we have to convert this into Newton. Accordingly, the AST which is required is shown in this particular column. Now, at the same time, we have to check whether it is satisfying the AST minimum criteria or not. And just now we have seen the AST minimum for this particular structure is 700 mm. So definitely for this particular case, we have to use this value because this is the maximum. Then this value. Then here onwards, we can use this value, this value, this value, this, and in the last, we have to use this value. Okay. So the AST actually which we are going to provide should be more than this one, that is 700, 700, and this is 756, and so on. So what we are doing is we are dividing the wall into different regions. So this is the first region, you can see from here to here. So if I talk about the height, so this is from top to 0.7 meters. Okay. So in top to 0.7 meters, we are using 8 bars of 125 mm diameter, which is going to give us the AST provided as 80.804.25. So you can see the AST required here, it is 700, 700, this is 756, and for this region we are going to provide 804.25 AST. Okay. Now in the second region, this is the second region. So second region is from a height of 1.5, 1.05 to 1.4. Here in this case, we are using 10 bars at 125 mm center to center, which is going to give us a AST of 1256.46, which is greater than the AST required over here. Okay. The third region is the largest region, and it is having the maximum steel. So so it is from a distance of 1.75 to 2.45. In this case, we are using 10 bars at 100 mm center to center, which is scattering about 1570.8 millimeter square, which is greater than the AST which is required over here. Okay. In the last region, we are talking about a distance that is 2.8 up to, say, straight away up to foundation. Okay. So we are using 10 dia bars at 125 mm center to center. Okay. So this AST which I am going to provide, it will be on the both side, it will be alternately, it will be provided, because this reinforcement is provided for the hoop tension, isn't it? So since the thickness of the wall is greater, that is 200 mm, so we can provide the AST on both the walls, and then we have to provide the spacing alternately. Okay. So I hope this is understood to everybody. ये ऐसा करते हैं. You can use even this for the GSR also, especially in case of greater depth. So 1 या 2 मीटर का है तो कुछ फर्क नहीं पड़ता, but if it is having a greater depth, in that case you can divide the entire region into different portions, and accordingly you can provide the steel so that the amount of steel can be saved over here. Okay. So I was talking about this. So this is the reinforcement details, and you can see the reinforcement bars, especially the one which are shown in the pink color. These are the circumferential reinforcement. Okay. So in the first region, we are using 8 mm dia bars at 125 center to center. In the central region, we are using 8 mm dia bars at again 125 center to center. Sorry, this is the vertical reinforcement. Okay. In the central one, this is 10 mm dia bars at 100 mm center to center. The vertical reinforcement we have already seen here. So this is the vertical reinforcement. We have to provide 700 mm steel. Okay, because this was the AST minimum, and for 700 mm steel, we can easily provide 10 mm dia bars at 125 center to center. Okay, so sorry, 8 mm dia bars at 125 mm center to center. So this vertical reinforcement also has to be provided in this particular fashion. Okay, I hope everybody has understood this. Are there any queries? Yes, students, are there any queries? Shall I proceed further?
Yes, sir.
इसका बहुत अच्छे से ड्राइंग बनाना ये मैं पोस्ट करूंगा, ठीक है? अभी टाइम वेस्ट मत करो उसको ड्राइंग करने में, ठीक है? Let us quickly take a very small part, that is the design of walkway. This we have already seen in the previous class. The same design has to be repeated. So generally the uh, clear walkway is of size 1 meter. Okay, so we are assuming the thickness of the slab or the thickness of the walkway as 100 mm. The span will be 1 meter. It will be subjected to different loads, that is dead load, live load and floor finish. So dead load, if you calculate, it is 0.1 into this will be 25. So this comes out to be something like 2.5 kilonewton per meter square. Okay, and live load we can assume this as 3 and floor finish as 0.5. So the total load comes out to be 6 kilonewton per meter square. And you can see this is a simple cantilever kind of a slab, so it will be subjected to UDL. Okay, so if you want यहाँ पर एक handrail होता है, so that load also you can consider if it is made up of some brick or maybe a concrete. Okay, usually a railing is provided, so we can take that load also. So the self weight will be simply W into L. So W is 6 into 1, so this comes out to be 6 kilonewton. This is the shear force, and the bending moment will be WL square by 2. So W is 6, L is 1, this is 2, so this comes out to be 3 kilonewton meter. Okay, so shear force 6 and bending moment is 3. This also we have received the same values in the previous design also, especially in case of pump house as well as in the aerator. So I'm sure if you remember last time, this was well within the range. Okay, so bending moment आया था आपका 3. Okay, this is 1.527, this will be 1000. What will be the value of D? Yes, what will be the value of D? This will be into 10 to the power 6. Okay,
44.34.
40.
4.34.
Okay, so this is sufficient. So this is capital D will be 100, small d will be 75. Okay, what will be the AST and what will be the AST minimum? AST minimum will be 0.24% of the cross section area. So this, I think this is 240 mm square. Give me the AST actual.
357.
350.
7.78.
Are you sure इतना आ रहा है? बेंडिंग मोमेंट कितना लिया?
So 3 into 10 was 6.
Someone please cross check this value. Is it 357?
Yes, sir.
Okay, so we will provide 357. How much will be the spacing of 8 mm dia bars?
One
140. So in place of that we can provide 125. ठीक है? So this is already covered, so I'm not going into much details of this, so please complete this. You can even check the slab for the shear also, because shear force values are already there with us. Okay, so the only part remaining is the foundation and the central shaft, which we'll be covering in the next class. Okay, so let me stop the recording. I hope there are no queries.